So we are starting with the Leibniz theorem.
This call is now being recorded.
Yes. So introduction, the Leibniz theorem of nth derivative. So with Leibniz theorem, we are more of looking at finding the nth derivative of a function. So we have an example: y is equal to x to the power n. How do we find the first derivative? We know that if you want to find the first derivative, the power comes down and we reduce the power by 1. So we are going to have nx to the power n minus 1. If you want to find the second derivative, we go through the same process. We have the n in bracket n minus 1 and we reduce the power by 1 again. So we are going to get x to the power n minus 2. If you want to find the third derivative, we do the same thing. We have n in bracket n minus 1, close bracket, open another bracket, n minus 2, x to the power n minus 3, because the power is going to be reduced. So we get to the nth derivative. So you do it till, so if it were to be a particular question, let's say x to the power 4, you are going to differentiate till you get a constant. Please, are we okay? So we have an example here, as I was saying. So the example says that use Leibniz theorem to find the derivative of y if y is equal to x to the power 5. So we are going to find the first derivative. We are going to have 5x and we are going to reduce the power by 1. So we are going to get 5x to the power 4. If you are finding the second derivative, the power comes down again and you reduce the power by 1. So you are going to get 5 times 4 x to the power 3. Finding the third derivative, we are going to have 5 times 4 times 3. The power is reduced by 1. So you have x squared. Finding the fourth derivative, we are going to get 5 times 4 times 3 times 2 x to the power 1. And when you are finding the fifth derivative, you are going to have 5 times 4 times 3 times 2 times 1. So for this particular function, you can do it up to the fifth derivative. Because if you get to the sixth, y6, you are going to have 0. So we are going to do it up to the fifth. So they are just applying the Leibniz theorem to do so. We have another example here. Use Leibniz theorem to find the derivative of y is equal to sine x. So we know sine x, it is an example of a circular function. Yes, so solution. Remember that when you differentiate sine x, we are going to get cos x. So the first derivative, we are having cos x. But we want to rewrite everything in sine form. So you can rewrite the function the cos x, which is the first derivative, as sine pi over 2 plus x. And then you find the second derivative of, so we have the first derivative is cos x. So our second derivative, we have cos x. When you differentiate cos x, you are going to get negative sine x. Negative sine x. And you can rewrite this as cos pi over 2 plus x, which is the same as sine 2 pi over 2 plus x. Remember that because the function was in sine, we want to leave all our derivatives in sine. That is why even when we get it in cos, we find another way to write it in sine, which is also the same thing. So when we find
Okay. So, Madam Charity,
yes, ma'am.
please. So the first one, the first derivative is y prime is equal to cos s, and we are saying that cos s is the same as sine into brackets pi on 2 plus x. So you can let them use the double angle to expand cos pi on 2 plus x. And they will see that when they use the double angle, the sine of pi on 2 plus x will be the same as cos x. So that's the reason why we are saying cos x is sine of pi on 2 plus x. And then the second one is negative sine x. And we are saying that that is also equal to cos pi on 2 plus x. So they can also use the same double angle to expand cos pi on 2 plus x. I hope they know what the double angle is. That is sine into bracket a plus b. So if my a is pi on 2 and my b is x, you can do the substitution. You know what sine 90 is, cos whatever, and then be able to show that cos on 2 and then cos pi on 2 plus pi on 2 plus x, which is sine pi on 2 plus x. So they can do that using pi, double angle. I don't know if they can do it right now or maybe, yeah. So the student can try that themselves. That cos x is the same as using
So please, are you okay?
double angle. And I hope they remember double angle. What is sine a plus b?
Please, madam, your line is breaking. We can't hear what you're saying.
Okay, so please try to tell them. If they can't hear me, maybe you can say
Hello.
it.
These are just
Yeah.
know the units we are working on.
Anthony, we didn't get you. We didn't get what you said.
I'm saying I just joined, so I want to know the units we are working on.
Do you need the units for something? I hope you will just follow what you are doing, or you want to read. You read from the notes.
Hello.
So I don't think please, I don't think you need the units. Just follow what we are doing. Then after that, you can go and read your notes, please. Because I don't know if you want to open the book, the I don't know, the whatever PowerPoint on your machine and be looking at. Then it means you will not follow. So please follow what you are doing. Thank you. Charity, please, you can continue. Hello, Madam Charity. Okay, so I think she's gone, but can somebody give us the expression for sine into bracket a plus b? What is the expression for sine into bracket a plus b? That's double angle. Hello,
Madam.
Madam Charity is back.
Hello, madam.
So sine into bracket a plus b is equal to what?
2 sine A cos A.
Eh? You take your time and then write it in terms of
Madam,
sine A, sine
madam,
B. Uh-huh.
is
Uh-huh. Yes,
sine
please.
A cos B plus cos B sine A.
Nah, it's sine A
Okay,
cos
so if
B
it's like that, then in place of
plus cos A sin B.
okay, so if it's like that, then substitute A and B, and let's see. So we know that sine into bracket A plus B is sine A cos B plus sine A cos B plus cos A sine B. So in place of A and B, you substitute pi on 2 plus x. So you're going to get sine pi on 2 cos s plus cos pi on 2 sine x. And what is sine pi on 2? Pi is 180. So pi 180 over 2 is 90. So what is sine 90? Sine 90 is what?
Madam, please, 1.
So please do that and let's do.
Sine
Sine
90
90 is
1.
1. So you're going to get 1 times cos s plus what is cos? So that expression, the first term will be cos s. And what is cos 90? Cos 90 is
Madam, cos
0.
90 is 0.
so it means that the second term will go to 0. So this means that cos sine pi on 2 plus x is equal to
Cos s.
cos s. So that's the reason why Madam Charity said that when you differentiate sine x, you are going to get cos s, and it's the same as. So you differentiate the second one, which is differential of cos s, which is negative sine x, and she said that that is also equal to sine into bracket pi on 2 plus pi on 2 plus x. So you can also do that one too, and then you see that it will be the same. Okay. So that is about what's laws. Let's continue. Your board is not showing, Madam Charity. It should be there. Madam Charity, yes, she's there. Madam Charity. Hey, Madam Charity. Okay, so she's not there. Let me see if I can do something. Ikra, come for the one. Madam Charity, we don't. Yeah, but we can't hear. So please. We are waiting for Madam Charity. So I'm using my phone. Madam Charity. So please, can you see my screen? I'm using my phone. Can you see my screen?
Yes, madam.
Yes,
Yes,
madam.
madam.
Hello. Okay. So as she was saying, she said that when you differentiate the cos x, you're going to get minus sine x. And this is the same as cos pi on 2 plus x. So you can also expand this one, cos pi on 2 plus x, using the double angle. And this is also the same as sine 2 pi on 2 plus x. Okay. So we want to find everything in terms of the sine pi on 2 plus x. So the first differential is giving us sine pi on 2 plus x. Second differential is giving us 2 pi on 2 plus x. So the third differential will be sine into brackets 3 pi on 2 plus x. And the fourth one will be sine into brackets 4 pi on 2 plus x. So this means that our nth differential will be the nth differential of y is equal to sine x will be sine into bracket n pi on 2 plus x. That is it. It's unfortunate I'm not by my laptop, so I cannot write. Madam Charity, what is happening? Where is she? Okay, so let's continue. But before we continue, I hope you remember what factorial is. Factorial. N combination. So, example, if I have n combination R, who can give me the expression for n combination R? Do you remember that one? Combination. Please, can you hear me?
Yes, madam, you can hear you.
Hello. What's the
Hi, madam.
expression for n combination R? Yeah. A. Okay, so n combination R is given as n factorial over R factorial into n minus R factorial. When you talk about factorial, it means that it is the number and then you keep on reducing it. So you reduce it by 1, the next one reduce it by 1, like that. So for example, if I have 4 factorial, 4 factorial is equal to 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So that is the meaning of factorial. So if you look at what I have here, I have n factorial, n with some is the exclamation sign, and we call it factorial. So n factorial is n into bracket n minus 1, n minus 2, n minus 3, continue. We continue like that. So n combination 2, for instance, will be n factorial divided by 2 factorial into bracket n minus 2
Madam, please,
factorial.
your line is breaking. Madam,
Hello.
please, your line is breaking.
Hello, Please, can anyone hear me?
Hi. Yeah,
Hello.
you can hear you.
Okay. Please, sorry, I was joining
Yes.
and all that, but it wasn't working. This too. Hello. Hello.
Yes, madam.
Yes,
Hello, Madam Charity. Hello, Charity. Charity, you are muted. Oh. Please unmute yourself. Hello, Charity, you are muted. Hello. Hello.
Hi. Yes, madam.
Yeah. I think Madam Charity is having some issues, so let me continue. See if I can do something till she comes. So I was talking about combination, and I said in combination R is giving us um very old one. It's giving us n factorial over 2 factorial r factorial into n minus r factorial. Okay. So as I said, n factorial will be n into bracket n minus 1, n minus 2, n minus 3, and so on. But because we have n minus 2 factorial as our denominator, we can end the top one at n minus 2 factorial, so that n minus 2 factorial down can cancel n minus 2 factorial up. Okay. And when it happens like that, the expression will be n into n minus 1 over 2 factorial. So we just want to look at the factorial. So, example, if I have products of two differentiable functions, u and v, and I want to differentiate, we know that by the product rule, we keep the first one, we differentiate maybe the second one plus, we differentiate the first one, then we keep the second one. So differential of uv is u, then uv differential u, and then v differential as u differential times v differential. The same function, we can find different derivatives. Then when you find different derivatives, it means that you have to keep your u, you differentiate your v1, which will be v2, plus, so it means that I have to differentiate the first term, which is u v1. So when I differentiate, I'll keep my u, I differentiate my v1, which is v2, plus the next one, I'll keep my v1, then I'll differentiate my u, which will be u prime. Then I come to the second term. I wish I can use my laptop, but I don't know what is happening here too. My laptop too is not working. So the next one, you move to the second term, which is u1v. So that one, you keep the u1, you differentiate the v, which is v1, plus you keep the v, then you differentiate the v1, u1, which is u2. So when you sum everything, please, can you see what I'm talking about? You know what is happening to my computer?
Yeah, madam.
And the screen is
Please, I
not
want to
even
ask a
showing
question.
well.
My screen is not even showing.
It's not showing well.
Madam, please, if you are using phone, then I would like to suggest that you turn it to the other side.
The landscape, rather.
I think we are okay now. Oh.
Okay. Madam Charity. Hello, Madam Charity. Is she here?
Network wahala.
Okay.
Yeah, I think it's okay now.
Madam, please, I wanted to ask for the second differential. Hello, madam.
Yeah, I'm here.
Please, I want to ask
for
the second for the second differentiation. Are you going to have 4 terms?
Yeah, you're going to get 4 terms. So you use product rule for the first term in
All right, thank you.
then use product rule for the second term in the inverse. Then you're going to get 4 terms. Then you see that some of them you can add them. So you're going to get U and then V2 plus twice U1, V1, then plus, I think, U2, V, and now U, V2. You're going to get something like that. I don't know if that's what you've gotten. I wish I can use my board so that I write on it. Okay. So in that, you will see that when you continue to find the third term, it's to end up like a factorial. So you're going to get like a combination. You're going to get the first term to be n combination 0, u to the power n, plus the second one will be n combination 1, u, so you will start increasing. U to the subscript 1, v subscript n minus 1, then it will continue to get the last term, which will be v subscript n. Okay. So we have an example. For example, if I have y is equal to s to the power 2 sine x, and I want to find the x differential. So to find the x differential, I have to treat this as u and v, where my u is Isra. My spectacles, where u is s to the power 2. So when you find the first differential, it should be 2s. When you find the second differential, it should be u. Then you come to the v. The u is our sine x. And remember, we know of the differential of sine x. We saw that the x differential of sine x sine into bracket n pi over 2 plus x. So if I find the first differential, it will be considered, which is the same as sine into bracket x over 2 plus x. Then when I find the second differential, that one to be sine into bracket. Please, my computer is separate. I want to use my computer. Oh, Maria, I don't hear me. Charity, where are you?
Connect. Yeah, madam. Yeah. Hello. Hello.
Yeah, please, I want to connect it
Hello.
to my laptop. Yeah. Yeah, Charity. Then you can start with.
Okay.
Madam Charity, you can start to. You can continue.
Yes, please.
All right, Madam Charity, please turn your phone to the other side. That is the landscape.
Okay, sure, I'll do that. Don't worry. Please, where did we get to? Hello.
Yes, sir. Yes, madam.
Please, where did you get to?
Can you switch to the next slide? Then?
We are talking about
Come again.
we are talking about the product rule.
This one. Please, is it this?
Yeah,
Yeah,
we were
this one.
here.
Okay. So the d dx of u vin. So when you do that, differentiation. We know from product rule, you will leave one, differentiate the other, plus you leave the other and differentiate the next one. So for this one, we left the u, we differentiated v, so we have v1. You are doing the first differential, plus now we will differentiate u and then we leave the v. So we are going to have u v1 plus u1 v. These are we okay? So if you are going to find the second differential, it is the same application. You leave one, you differentiate the other. So for the first part, they are going to apply the product rule, and the second part is the same thing. So in the second differential, you are going to have three terms. Yes, so for the first side, you leave the u, you differentiate v1, you have v2, plus now you leave the v1, you differentiate u, you have u1. So you have u v2 plus u1 v1. And then you do the other side, which is u1 v. When you differentiate the v, you would have u1 v1 plus now you leave the v, you differentiate, you have u2 v. And then when you do your algebra correctly, you're going to get u v2 plus 2u1 v1, because we have two of that terms there, plus u2 v. And we are saying that this is also the same as u v2 plus 2 combination 1. If we punch 2 combination 1 on our calculators, we are going to have 2. And we know how the solution is done. When you have n combination r, it's equal to n minus r. Is it n minus 1 or n minus? I'm coming.
I don't charity.
Yes, please. Do you need to
The latter part, I think, if you can explain that part for me. That is the u
saying
v2
that
plus.
they are saying 2 is the same as 2 combination 1. 2
Okay.
combination 1 on the calculator is the same as 2.
All right. I get
Please,
it.
are we okay? So that is how they've written it in combination form. That is all. Is are we okay?
So I just explained combination to them. That 2 combination 1 will be 2 factorial divided by 1 factorial into 2 minus 1 factorial. And then I said 2 factorial will be 2 times 1 divided by 1 factorial is 1. And then 2 minus 1 is also 1. So that will also be 1 factorial. So you have 2 times 1 divided by 1 times 1, which is the same as 2 over 1, which is 2. So that's the reason why we are writing the 2 as 2 combination 1. I hope it's fine.
Yes, please.
Okay. So we have an example here. We are going to be using the Leibniz theorem to solve. So our function is y is equal to x squared sine x. So we have two different terms here. We have x squared and sine x. We want to use the product rule to solve it. So we want to find the yn, the nth derivative. So what we want to do is that we want to make u to be equal to some. You remember that this side we had u and v. So we want to apply the same rule here. So here we want to make the u to be equal to x squared and then v to be sine x. Please, are we okay? So when we are going to differentiate our u, so when you find the first derivative of x squared, we are getting 2x. And the second derivative of 2x of x squared is going to give us 2. For u, we are going to end on the second derivative, because if you find the third derivative, it's going to give you 0. So it ends on the second. And for v is equal to sine x, we want to find, first of all, we want to try and solve for the first derivative, second derivative, and then we find for the nth derivative for the v n, because remember that sine x is a circular function, so it doesn't stop. So it's continuous, so it doesn't stop. So what happens is that when we find for the vein 1, we are going to get cos x. Remember we did it earlier. And then when we apply double angles, we can rewrite it as sine in brackets pi over 2 plus x. When you find for the second derivative of sine x, we are going to get negative sine x. And we can rewrite this as sine in brackets 2 pi over 2 plus x. That is a double angle. So we realize that as you are moving wherever, if you check the first derivative, second, there is a pattern there. So you can still find the nth derivative, which is going to be sine n pi over 2. Because you realize that for the first derivative, we have sine in brackets pi over 2, which is the same as 1 pi over 2 plus x. When it was second derivative, we have sine 2 pi over 2. So realize that the nth derivative is going to be sine or open brackets n pi over 2 plus x. So we now know for our Vn and our u, our first derivative for u and our second derivative for u. Now we are going to apply the Leibniz theorem to find for the nth derivative. So dn of x to x squared sine x over dxn. So we saw something here down here that when you want to find the nth derivative using the Leibniz theorem, we have u vein n plus n combination 1 u1 vein n minus 1 plus n combination 2 u2 vein n minus 2 till we get to the last term. So remember that we now know what u is, we now know what vein n is, we now know what u1 is. We will have to find vein n minus 1. And remember that u is ending on the second derivative, so we have to find vein n minus 2 as well. So let me use the board quickly so that we check something. So we know for our u to be equal to x squared and u1 is equal to 2x. Sorry, 2x, and u2 is equal to 2. We are ending on the second derivative for u. And now we know for vein n to be sine open bracket n pi over 2 plus x. So now we have to find our vein n minus 1 and then vein n minus 2. So wherever you see n, for when you want to find vein n minus 1, wherever you see n, now it's not going to be just n, it is going to be n minus 1 all in brackets pi over 2. And wherever you see vein n minus 2, for the next one, wherever you see n, you replace it with n minus 2. So that is what I have here.
Madam Charity.
Yes, I'm listening to you, please.
Madam Charity.
Hello. 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 Hello.
Yes, madam.
Please,
Please, I'm listening to the person talking.
please, I would like to pass this short notice to
This what?
those in Wesco UCC. Please, your lecturer is in.
Oh, okay.
Thank you.
Can I proceed?
Yes, madam. Please, yeah, Wesco UCC. Please, your lecturer is in, so you can join the link. Thank you.
Okay. So from what we have here, we are finding for the nth derivative of the function. So we know that the first term would be u vin n, and we know our u is x squared. Our vin n is sine n pi over 2 plus x. That was the first term we have here. Plus the next term will be u one vin n, but we have a combination which is n combination 1. N combination 1. So for that term, we would have our u1 is 2x. When we differentiated the first derivative of u, we would have 2x. And for vin n minus 1, we would have sine open bracket n minus 1 pi. Remember earlier I said that this time wherever you see n, you replace it with n minus 1 all over 2 plus x. That will be our vin n minus 1. And for the third one, we would have n combination 2. We would have u2. u2 here, we said it is 2. And then our vin n minus 2 becomes sine open bracket. The top becomes n minus 2 pi all over 2 plus x. So for this function, we would have 3 different terms because our u ended on the second derivative. So we have 3 different terms. So if we want to simplify, we know how to write combination. So we know that n combination 1 is the same as, let's do it here. We know that if we have n combination r, it is the same as n pi all over r factorial, n minus r factorial. So this time we have n combination 1. It is the same as, so wherever we see n, we put n factorial there all over r. Our r is 1. Our n here is n minus 1, if I'm right. So we would have n, this one we can write it as n, the numerator we can write it as n open bracket n minus 1 factorial all over 1 factorial is the same as 1, so we would have n minus 1 factorial. This goes with this, so at the end of the day we will just have n. Please, are we okay? So that is the reason why when they simplified for this side, when they simplify, if you check the second step, when they simplify for the second term, they had n 2x sine. The same thing when we have n combination 2. N combination 2, let me do that one too, so that you see what we are going to get. N combination 2, we have n combination 2. So we have n factorial all over. Our r now is 2, so n minus 2 factorial. So the numerator we can rewrite it as n minus 1 open bracket n minus 2 factorial all over 2 factorial is the same as 2 because it's 2 times 1, sorry. So we have n minus 2 factorial. So this goes with this, so we would have, we'll be left with n minus 1 over 2. Yes, we have this. So that is what we have here when they did the simplification. That is what they had at the last term. So we have n combination 2 to be the same as n open bracket n minus 1 all over 2 times 2 sine open bracket n minus 2 pi over 2 plus x. So in the next step, what happened was that for the last part, the denominator 2 cancel the 2 over here. So when you do that, you rewrite it and you are going to get the nth derivative of x squared sine x to be x squared sine n pi over 2 plus x plus n 2x sine open bracket n minus 1 pi over 2 plus x, and the last term is n open bracket n minus 1 sine open bracket n minus 2 pi over 2 plus x. So this becomes the nth derivative when we are using the Leibniz theorem to do it. Please, are we fine? Yes, we are fine.
Hello, madam. Please, I want to know the main idea about the Leibniz theorem. The
Main
main idea
idea.
when you are given a question for you to solve, like this one, like Leibniz theorem, like send because I just joined along the line.
Hey, so I have to start all over again.
No, madam, I want to say idea. No, I said the
The
idea. No.
idea, hello, let me give you just a second. The idea of Leibniz is to find the nth derivative of a function you are being given. Please, are we okay? So if you are given a function, the idea of Leibniz is to solve it in a way that you can find the nth derivative. So that when maybe n is given, if you have the Leibniz, maybe the nth derivative of a particular function, it is like you have an equation in terms of n. So when you have a follow-up question, maybe when you are given n to be, let's say, 20, you can do it easily, because you can't, let's say you have a question and you are being asked to find the 20th derivative. You can't do it one by one, so it will be stressful. So the Leibniz theorem is there so that you can generate the formula, so that when you have n to be a particular number, you just fit it in and it becomes easy to solve. Please, are we okay?
Okay. Idea number.
Okay. So it is just finding nth derivative of a particular function, so that maybe if you are being asked to find maybe the 10th derivative, the 15th derivative of a particular function, it becomes easy instead of you going through the stress of differentiating it one by one until you get the 15th derivative. Yes, so that is it. So we have another example here, and we are being asked to use Leibniz theorem to do so. So we want to also find the nth derivative. So this particular function, we have more like 3 different terms. We want to do it stepwise so that you don't get confused. So for the first part, where we have open bracket 1 minus x squared close bracket y2. Then we have the next one plus xy1, and the next one is plus y equal to 0. You are being asked to differentiate it n times. So the idea is finding the nth derivative. So the same way we did, we are going to find our u and v for each particular term. So if you look at the first term, we have 1 minus x squared y2. For that one, we are saying that we are making our u to be equal to 1 minus x squared and our v to be y2. Most of the time we make the function that can be easily differentiated to be our y. The function that can be easily differentiated. So let me come back here. For this particular function, the term that we can easily differentiate will be the x squared. So that is what we make our u. And the one that will be a bit complicated, we make it our v. So that is the same thing here. The one that is easily differentiated will make our u, and the complicated one we are making our v. So we are making u to be 1 minus x squared and the v for the first term to be y2. And then when we come to the next term, we have xy1. We are making u to be x and v to be y1. We are doing it simultaneously. So we are going to apply the general formula. So this one, you are also going to go through the process of finding your U1, you find your U2. So what will be our U1? Please tell me, what is U1 for the first side? Please, I'm waiting. When U is equal to 1 minus x squared, what is U1?
Negative 2x.
Minus 2s.
Minus 2x. What about U2?
2.
What will be U? Is it 2?
Minus 2.
It will be negative.
Minus 2.
Minus 2. Negative 2.
Okay. And then let's find our vein. Our vein is what? U2, right? Let's find vein 1. What will be vein 1? What will be vein 1? The differential of vein 1 will be what? The differential of vein 2 will be what? What will be the differential? What will be the differential? So you have your vein to be Y2. What is vein 1? I'm sorry. What is vein 1? To be
Something with dy
Y2
dx.
plus 1. So it will be Y3. Are we okay? What will be vein 2?
No, madam, this part, are we differentiating it or
Yeah,
how
differentiate.
are we doing it?
Yeah,
So
differentiation.
the vein, madam, the vein is y. Is it y to the power 2 or y2?
Y2, as in Y subscript 2. As in the second differential. Do you get what I'm saying? Hello.
Madam,
Madam, okay.
So your vein 2 would also be Y2, your initial plus the 2. So you have Y4. So
madam,
if
please,
you
I'm not
want
getting it too. Madam,
we
and
want
she has
to
said
find we want to find please don't be confused. I beg you. You want to find
Madam, please bring the question. Let's see. Show your board and let's see.
I have.
I want to see
This is
the question itself. Like,
okay. This is the question. This is the question we are working with.
okay, so the question here is here, and we want to find the nth derivative of this question. And this question, you can see that we have three terms. The first term is 1 minus x squared in a bracket y subscript 2. That is the first term. And the second term is x times y subscript 1. That is the second term. And the third term is y. Now we want to find the nth derivative. So to find the nth derivative, we want to use the product rule. So we can see the first term, which is 1 minus x squared in a bracket y subscript 2. It's a product of two differentiable functions. So we use the product rule here. And the Leibniz rule for the product rule, we saw that it is, Madam, go to the slide before this. No, up, down. No, down. Okay, so I think it's here, this one. The end, oh no. The end derivative formula.
Is this one? It's here.
The end derivative, it says that if you have two differentiable functions, and you want to find the nth derivative, it is given by u, the nth derivative of v, plus n combination 1, the first differential of u, the n minus 1 derivative of v, plus n combination 2, the second derivative of u, the n minus 2 derivative of v, up to the last term, which is the nth derivative of u times the v. So for our example, madam, go to the example. For the example given, we treat the first term, as a differentiable function. So we'll but I think in the note somewhere it says that choose your u such that after some few derivative, it gets to 0. So looking at this, you can see that if I choose 1 minus s to the power 2 to be my u, when I find the first differential, it will be minus 2x. The second one will be minus, the second one will be what?
Minus 2.
So the first minus 2, minus 2, and the last one will be 0. Okay. So we'll let 1 minus s squared to be our u, and then v subscript, y subscript 2 to be our v. So in the theory given up here, I have to, first of all, find the first differential of u, the second differential of u, and then and it continues. So my u is 1 minus x to the power 2. The second differential is square. It's not there.
They didn't
So madam,
solve it.
please, you give us your plain board. Okay, so give us the plain board. So we are solving them one after the other. We are solving the first term, then after that we'll solve the second term. So let u be equal to, madam, let u be equal to 1 minus. So that is my u. Okay, so let's find the first differential, which is u sub 1. So u sub 1 is equal to minus 2x. And then u sub 2 will be equal to minus.
You've done it.
U sub 2 is minus 2.
Yes, please. It's here.
We can see. Okay. So that is it. Then you let your v be equal to y subscript 2. That is your v. So what will be your v subscript n? That is the n derivative of v, because we know that in the formula we need the n derivative of v. So nv will be y subscript 2 plus n. Then v, so we are reducing. We know that when you find vn, the next step I have to reduce my v by v subscript by 1. So I have to write vn minus 1. Vn minus 1. So when I do same to the right, I'm going to get y subscript 2 plus n, which will be y subscript 1. Please, it will be 1 plus 1 plus n. Please, are you following? Student, please, are you following?
Yes, madam.
Yes, madam.
Okay. So this is n plus 1. This is delaying. Okay. So the next one will be V minus 2, which will be V subscript N. That is the V minus 2. Okay. So you go back and substitute this into the formula. Madam Charity, let me write this. So please stop sharing and let me share my screen for this one.
Okay.
Yeah, me yeah do. So my son be joining me. Omo could be an aden school for you at this stepping.
Madam Enyezo.
Yeah. Serious to Mr. Okay, so the function, the first term is 1 minus x squared ds y subscript n. This is the first term. So, and the n derivative of u times v over du. Madam, the formula is u what? U v subscript n, right?
Yes, please.
The formula is, Madam, try to give me the formula. The formula is
For everything. The Lebanese.
yes.
Madam, is it the Lebanese?
Lebanese is.
So we
Yes,
have
please. The n derivative.
we have u vin n plus n combination 1
U v n plus
n
combination
combination
1 u1 v n
minus 1
plus n
plus
combination
n combination 2
u2 v n
n
minus 2
minus
like that. So for this one,
yes,
as I said, you let your u be 1 minus x squared so that your first differential will be equal to minus 2x. Then the second.
Madam, please, the screen is off.
Madam, please, you stop sharing.
Your screen.
Is it showing now?
No.
Yeah. Yes, please.
Yes,
Is
madam.
it showing
It
now?
is showing. It is showing.
Yes, please.
Yes.
Okay. Okay, so we have the first term. So this one, as I told you, the function, they are supposed to be three terms. So the first term is 1 minus s squared y sub n. So we are treating that one. It's a product of two differentiable functions. So we are using the Leibniz for the second term, which is x y sub, I think, n minus plus 1 or so, something like this, plus 1.
Madam, your line is breaking. We can't hear you.
The line is breaking.
-2 and so on.
Madam, we can't hear you.
Hello. Madam.
Hello, madam.
So here
I
I
can't
have
hear her. I'm
to
trying to
find.
get her on.
Then my
I can't see.
Hello, Madam Charity.
Hello.
Madam Charity, please,
Yeah.
if your network is good enough, please kindly tell Madam so that you can continue for us, because I think the network at Madam's side is not good.
I'm trying to. But please, do we understand what she was trying to communicate about finding the using product rule you have to do for each term. Then when you are done with each term, then you put them together and you would have the nth derivative. Hello.
Hello.
Please, are we okay with the explanation?
No.
Okay, I'm coming. The network in the Okay. Let me go back to the slides. We have this is what we have. This is what we have. This is what we have. Okay, so you see, for the first term, we said we made u to be equal to 1 minus x squared. I believe we followed through and we saw how to find for the first derivative of u and the second derivative of u for the first term. Are we fine? These are new responses. Are we fine with that one?
Madam, for the U there, I'm okay, but the Y,
Yes.
I know
Which
Y
one?
is an implicit function. Know the, what do you call it? We are using the product rule. And the
Okay.
Y2 rather.
Mm-hmm.
So Y is an implicit function. Now, if you differentiate that one, you will get dy dx. So I
Exactly.
don't
The
know
y
why we
is
are
the
getting
same as y prime, isn't it?
it is.
It's like you have d of you are differentiating with respect to what?
X.
X. So we have y2. Let me go to the board. I'm coming. I want to erase everything. Okay, so you have your vein to be equal to y2. Are we okay with it? Now we want to find derivative of y1. You are saying that this is an implicit, so we are differentiating with respect to x. So it should be this, isn't it? Hello? You can connect.
Yes.
So what are you are trying to imply that it should be 2y dy dx. Is that what you are trying to say?
Yes, madam.
This is not correct. The function is not y
So
squared.
No, you get this in y2 divide dx.
Okay, so I'm back. Hello, can you hear me? Please, can you hear me? Hello.
Yes. Hello.
Yeah. So I'm back. So I just saw that somebody is saying that when you differentiate V, you are, please know, this is the Leibniz rule. So we are treating the U, they're just using U and V. So this one, we don't use that method. So, but when you differentiate U subscript N, the U subscript N here is not Y, sorry, Y subscript N here is not Y squared. So we are treating them as two differentiable functions. And okay, so I think I wrote something. So I said that your U will be, so you are choosing them as U and V, where your U is 1 minus x squared. And when you find the first differential, here we don't bring the differential up, it becomes subscripts. So U subscript 1 will be minus 2x. The second one will be...
This madam, your screen is on screen.
All right, then. You mean network is there? It's not helping. Okay, so please, I'm coming. Okay, so this is the formula for the Leibniz end differential. So you choose your U to be 1 minus x squared, and then the first differential will be minus 2x. The second differential will be negative 2. Then you choose your V. So this is two functions, U and V. So I'll choose one to be my U and one to be my V. So my V will be the Y. So you see that I have 1 minus this. This is my U and this is my V. So my V is Y subscript 2. Sorry, this is supposed to be 2. This is supposed to be Y subscript 2. So in the formula, I have to get V subscript N. So V subscript N is going to be Y subscript, I have already 2, then plus my N. So it will be Y subscript N plus 2. And in the formula, you can see that, so the first term is U times your V subscript N. The second one is N combination 1, the first differential of U, and then N minus 1 differential of V. So N minus 1 differential of V will be Y subscript N plus 1. So we are quoting the formula, please. So that will be Y subscript N plus 1. So I'll go and then substitute. So I'll have it here, N combination 1, the first differential of U, which is minus 2x, and then the N minus 1 differential of V, which is N Y subscript N plus 1. So I go to the formula again. The next one is N combination 2. So I have N combination 2. Then the second differential of U, which is negative 2. I have negative 2. And then the next one is N minus, so this is N subscript, V subscript N. This is V subscript N minus 1. So the next one will be V subscript N minus 2, which is Y subscript N. So I go back, I substitute them in the function. I have N combination 2, the second differential of U, then N minus 2 differential of V, which is Y subscript N. So this is it. Then you can open it, you can expand everything. So this will be 1 minus x squared yn plus 2. Then what is n combination 1? I just told you that n combination r is n factorial over r factorial into n minus r factorial. So if I have n combination 1, this will be n factorial over 1 factorial into n minus 1 factorial. And this is the same as, so my n factorial is the same as n into n minus 1 factorial divided by 1 factorial into n minus 1 factorial. N minus 1 can go with this, then I'll be left with n over 1, which is n. So n combination 1 is n into minus 2x into y minus 1. Then I go to n combination 2. So n combination 2 is n combination 2 is n factorial divided by 2 factorial into n minus 2 factorial. And this is the same as n into n minus 1, n minus 2 factorial, then 2 factorial into n minus 2, this factorial. So this n minus 2 will go with n minus 2 factorial. So I'll be left with n into n, so I have plus, oh, this is plus n into n minus 1 over 2. This is the n combination, that then into minus 2 times y subscript n. And we should be able to expand this one. So this is over 2, not over n, this is over 2. So even this 2 can go with this, and I'll have negative something here. This is negative. This is for the first term of the question. Then you come to the second term. So you will end here because you know that when you differentiate negative 2, it will be 0. So the next term will be 0. So this is where you end for the first term. Then you go to the second term. The second term is this. This one too is a combination of 2 differentiable functions. Okay. So you choose your u. So that one too, you choose your u and then your v. So your u will be, Madam Charity, is the question correct? Is it x times y subscript 1? Madam Charity?
Yes, madam.
Madam Charity?
Madam.
The second term,
Yes,
is
madam.
It x times y subscript 1?
Yes,
Okay.
please.
So this one, I will let my u to be x, and then my v to be y subscript 1. So when I differentiate u first, I'm going to get 1. So I will not differentiate again. Then this one, my vn will be y1 plus n. Then when I differentiate again, which is vn minus 1, this will be y subscript n. So this one too, I'll go to the question and then start with my, I'll go to the formula and start with my substitution. So dnx over is uv, sorry, uv over dx squared will be, so the formula I have u times v subscript n. So my u is x, and then v subscript n is y sub 1 plus n plus n combination 1. Then I'll have the first differential of u, which is 1, and then the next differential of this, which is y n. So this is what I will end for this, because I know that the next term, if I find the next term, it means I have to find the second derivative of u, which will be 0. So the nth differential for the second one is this. Then I go to the last one, which is y. Okay, so the last one is y. And this one can be seen as 1 times y. So my u is 1, and then my v is y. So my v subscript n will be y subscript n. I don't have to differentiate my u, because when I differentiate, I'm going to get 0. So for this one, when I go to the formula, I have d n over x squared of uv. So this one is supposed to be x, y, 1, and y will be equal to, so I'll have my u, which is 1, times the nth differential of v, which is y sub n. The next terms will give me 0. So this is the nth differential of the third one. So I have to combine all these three. So I will have the first term, the first one plus the second one. So the first one is here, plus the second one is x, y subscript 1 plus n, plus n combination 1, you know, is n, right? So I'll have plus n y n. Then I'm done with this one. So I come to the last one, which is plus 1 y n. Then you simplify. So you can simplify this. Is it understood? Do you understand this one, small? Hello, students.
Yes, madam. The first differential is our
Is it
problem.
okay? The first differential is what? The first differential of
Madam,
what?
I did not understand the first differential.
The first differential of what?
The 1 minus x squared multiplied by y sub 2.
Is this one? So the first differential of u is minus 2x. Is it this one?
Yes, madam.
And you are saying this is a different, this is a problem.
How it is substituted in the formula?
But is it not here? It is here. It is minus 2x. It's in the formula. How did I substitute it in the formula? It is n combination 1. Then I substitute the first differential of u, which is minus 2x. Is it this one?
But I'm going through it. So
Madam Charity.
Yes, madam.
So that is the solution. So maybe you can continue. Or any other person with any question or something. Edwina.
Madam, the formula is looking like something else. We can't even capture the formula the way it is. But be say, I am when I be say, until we are not feeling tough, to be honest.
So how can we help? So I think how the formula, even Madam started proving the formula. She proved it too. It's just that maybe you decided not to pay attention. Because she proved the formula. She started with the differential of u and v.
Madam.
Yes.
For first term, the example we just solved, someone was with the notion that for the vein, the vein being equal to y sub 2, he was saying its differentiation should be y2
Eight differential. Eight nth differential. Madam, catch and say we are finding the nth differential. Nth differential, and can he find the nth differential from Has he learned from anywhere how to find nth differential of a function? This is nth differential. It's not first differential. It's not second differential. It is nth differential. Nth and the n that you don't know. We are saying that v is equal to y. Even if I say that v is equal to y, then my nth differential will be y sub n. That is it. If my v is equal to y subscript 2, then the nth differential, it is not first differential, it is not second differential. So if the person is thinking about what he knows, the first and second differential, no, it is not the first and second differential that you know. So the nth differential of this will be yn plus 2. And when we talk about nth differential, thus we are talking about, so if my v is equal to y, then the nth differential, I'm talking about differentiating v n times, which is the same as the nv over the x to the power n. And this we are saying is equal to the ny over the xn. And he's saying it's not correct.
Madam, I didn't. Hello, madam. I thought this thing, because we are using the first differential for u and second differential for u, it also apply to v. So since it's the nth differential, okay.
In the formula, we have nth differential of v.
Madam, so okay, let's go. Okay.
Okay. So if this is my v, if this is my v, this is my v, then my nth differential is this. And this can be written as the nv over the xn, which is the same as, so this one, the power will be this n plus 2 y over the x n. This is what we are talking about. So it's the nth differential, please. The v, we are looking at the n. So the v starts with the n differential, and then the u starts with the function itself before you move on to the second. And so this one, it follows something like the binomial theory. It looks like the binomial theory. And I hope you know the binomial theory, how to prove the binomial. It also uses the same thing. So if I have a plus b to the power n, then I'll have a something, maybe a phi, but I know we have some combination and so on. So the a will be reducing the power and then the b will be increasing. So it's the same approach that we use here. Similar approach. So please, the v is the nth differential, but the u, you start with the first differential. Thank you. Madam, please continue.
Okay.
Let me stop sharing my screen.
So the next thing we'll be looking at is the Leibniz rule. We are now done with the theorem. Now we want to look at the Leibniz rule. So we have, it says that let a and b be constant if f and the derivative of f with respect, the partial derivative of f with respect to the x are continuous on the rectangle what we have there. Then we are saying that if you want to find I of x, it is you find the integral with limit a to b f of tx dt. So for the Leibniz rule, what we are trying to do is that we would have a function, yes, a function in terms of two variables. What we want to do is that their question, if you are being asked to find the derivative of I of x, You first of all find the partial derivative of that function with respect to x. Then when you are done, you will come and find the integral with respect to t or the other variable. So this is what we have. So if you want to find the partial derivative of if you want to find the derivative of I of x, sorry, it is the integral of a to b, the partial derivative of f of that function which you'll be given, which is in terms of two variables, t and x. Then when you are done, you will find the integral with respect to t. So first of all, you have the function. You differentiate, you find the partial derivative with respect to the x. Then, and remember that you know by the question, because the question is in terms of we are finding partial derivative, the derivative with respect to x. So your partial derivative should first of all be in x so that your integral will be in the other. So we have an example to explain this. Please hold on. Yes, so we have an example to explain the Leibniz rule. So we say that if f of x, remember that the function is in terms of x. You are asking of f of x is equal to with 1 to 2 cos tx over t dt. We are being asked to find the derivative of f of x. So for Leibniz rule, what we are doing, the function that we've been given here is in terms of two variables. We have x and then we have t. And we are being asked to find the derivative of f of x. So the first thing you are going to do is that since it's a function of two variables, you take the partial derivative of the function. If you want to find derivative, first of all, you take partial derivative. And when you find the partial derivative of your function given, that is cos tx over t. You find the partial derivative with respect to x of tx over t. What do we have? Is any idea? When you differentiate cos tx over t with respect to x, in this case, our t becomes a constant. So what will be your your differentiation?
First, you differentiate the cos and then the function within the cos again.
Okay.
And then we multiply.
So
So
what
when
are
you
you going
differentiate, you get minus sign
minus
sign of the tx, and then you differentiate tx with respect to x, and that will give you t, and then you multiply.
okay. What about the t down there? The t down there is a constant, so you can factorize it out. Are we okay? So let me go to the board. So we have partial derivative with respect to x of this function cos tx over t. So what you do is that the 1 over t is a constant, so you can bring it out and you focus on the cos tx. When you differentiate cos tx, you are going to get negative sine tx. This is a function within a function. So when you are done, you come and work on what is inside, which is tx. And when you do that with respect to x, you are going to get t. So you are going to have negative t sine tx over t. This t will go with this t, so we would have negative sine tx. Please, are we okay? So when you are done finding the partial derivative with respect to x, now we know that our function is now reduced. We would have integral with limits 1 to 2 negative sine tx dt. Now the next step is that you are now going to find the integral. You are now going to integrate with respect to t. You see, the first one, you found the partial derivative with respect to x. The integration will be with respect to the other variable. So the partial derivative was with respect to x. Now you are going to integrate with respect to t. So when you integrate negative sine tx, what are we going to get? Negative sine tx. Please, I want to hear from you. When you integrate negative sine tx, what do we get?
You get cos tx, and then you differentiate the function and then divide. Yeah,
Okay,
because
so
it's integration, you divide.
in this case, our x becomes a what? When we are integrating with respect to t, x becomes a constant. Okay. So when you integrate negative sine tx, you are going to get cos tx over x. And remember that the limit is for t. So your limit is t equal to 1 and t equal to 2. So when you get that, wherever you see t, you put your limit in there, and you are going to get your derivative to be cos 2x minus cos x all over x. Please, are we okay? So that is about the Leibniz rule. So Leibniz theorem is different from the Leibniz rule. Leibniz rule is telling us that when you have a function in terms of two variables and we want to find the derivative of one of them, you first of all find the partial derivative with respect to that variable. When you are done, you integrate with respect to the other variable, and you put in the limit and you get your derivative for that function. So assuming the question was f of t is equal to integral from 1 to 2 cos tx over t dx. In this case, you are going to find the partial derivative with respect to t instead, because your question was asking of f prime of t. So your first partial derivative will be with respect to t, and then you come and integrate with respect to x, and your limit will be for the x, so that at the end of the day you have f prime of t to be what you have there. So at the end of the day, remember that your trick should be that when you are done, your derivative should be in terms of the variable you are being asked to find. So remember, this one we are being asked to find it in terms of x. So remember, our final answer, they are all in terms of what? X. So there is no t variable in there. Please, are we okay? So when you find the Leibniz rule, you have to be careful. First of all, you find partial derivative, and then you come and integrate. So that is for the first example. So we have another example here. Yes. Integration via differentiation under integral sign. So this example, we have I of alpha is equal to integral limit 0 to infinity, positive infinity, dx over alpha squared plus x squared is equal to pi over 2 alpha. So for this particular question, they solved for the integral and they had pi over 2 alpha. Our function, the function, if you look at the question, was 1 over alpha squared plus x squared. They've done that. And they are telling us that we should use what we have been given to show that integral of 0 to positive infinity dx all over open bracket alpha squared plus x squared all squared is equal to pi over 4 alpha cube. via Leibniz rule. So we want to show that what we have at the beginning would end up with what we have at the end using Leibniz rule. So we are going to start with what we have if I of alpha. That is what we are starting with. And I stated earlier that for Leibniz, your I of alpha will tell you what to do first. So because the function is in alpha, our derivative, we want it in alpha. Our first thing we are going to do is you find the partial derivative with respect to what? What will be the partial derivative? It will be with respect to what? Hello.
It will be with respect
Hello.
to alpha.
Okay. So it will be very good. But remember that this one, it is equated to pi over 2 alpha. So whatever you are doing on the left hand side, you should do on the right hand side. So the left hand side, we have integral of 0 to infinity dx over alpha squared plus x squared. And it is being equated to pi over 2 alpha. Look at the left hand side carefully. You realize that for that particular function, it is in terms of two variables, and the one on the right hand side, it is in terms of only one variable. So for the left hand side, you are going to find the partial derivative with respect to alpha, and the right hand side you find the derivative. It will be a full, it won't be partial because it is just a function in one variable. So when we do for the left hand, let's solve for the left hand side. For this one, we are going to use quotient rule. So when we solve, what are we going to get? I want the feedback from you. When you find partial derivative with respect to alpha of 1 over alpha squared plus x squared, what do we get? I want you to give me the answers. What do we get using your quotient rule? So in this particular one, x is a constant. Is that
When
how
you
we get it?
when you differentiate the top one, the one, because it's a constant, it will give you 0. So whatever you multiply to the 0
No,
will give you
no,
0.
no, we are not working it like that. We are using quotient rule. Or better still, you can move what is at the down up and then it will be to the, let me write it. You can't do the differentiation like that because if you do it like that, you are saying you are getting 0 and it is wrong. So what do we have? We have with respect to alpha of 1 over alpha squared plus x squared. We can rewrite this to be, you can write it this way, minus 1. So that when you use the implicit, you have negative 1, maintain what is in here, you reduce it, times, now you focus on what is inside. So when you differentiate this, you're going to get 2 alpha. This is a constant, so you get 0. So you can rewrite it as negative 2 alpha. We want to bring this down. So you have x squared plus alpha squared plus x squared all squared. So this is what you are going to get when you differentiate. Find the partial derivative of 1 over alpha squared plus x squared. You can also use the quotient rule where you equal to 1 and your v equal to alpha squared plus x squared, and you follow the quotient rule, and then you will end up with the same answer. Please, are we fine?
Yes, madam. Madam, please, my brother Koku Buama it's the same thing that he was doing with the quotient rule. But I think we didn't allow him to, and that's why he couldn't explain it.
The quotient rule we can do it. Quotient rule, so we
Except
have
my brother.
1 over x alpha. So quotient we are saying that you will have this. This is the same as this. So if you want to differentiate, it should be vein u1 minus u vein prime over vein squared. So our vein is the entire of this alpha squared plus x squared. And differentiate our u, we are getting 0. Sorry. Hey. You are getting 0 minus your 1. When you differentiate your vein, we are doing it with respect to alpha. So we are going to get 2 alpha. X will be a constant, so it will give you 0, all divided by the square of this. So at the end of the day, you still get the negative multiplying this. You are still going to get what I had at the top here.
Right, this is what I started and it didn't allow me to continue.
You said you get 0 at the top.
No, I said you differentiate the constant 1 and it will give you 0. So when you multiply it down by the 0, the whole side will give you 0. And then you come and take the denominator and then differentiate. But it didn't allow me to
So you
finish.
are using the quotient rule. Please, are you using the quotient rule?
Exactly.
Okay,
That's why
apologies.
you
I
did
didn't
it.
hear you. I'm sorry, please. Please, are we okay? So on the right hand side, we have, what do we have? Is it 2 pi? Hello. So on the right hand side, we said it is pi on 2 alpha. So we are doing it. This is what we had for the left hand side. On the right hand, we have 2 pi over alpha. We want to find the derivative with respect to alpha. So in this case, 2 pi is a constant. We want to deal with the alpha. So you have 2 pi times this will give us -1 alpha minus 2. So we can rewrite this as -2 pi over alpha squared. Please, do we agree? I did something else. Hey, it's pi over 2 alpha. I did something else. So we have pi over 2 alpha. So in this case, our pi on 2 is a constant. Alpha will come up. So we want to differentiate. We would have this -1 alpha minus 2. So we would have negative pi all over 2 alpha squared for the second side. What we are trying to achieve is what we are given. We want to do it in such a way that we would have what they are saying. They are saying we should show that this is true, or if we have this, then we have that. So after getting our differential for the partial derivative for the left hand, we had -2 alpha all over alpha squared plus x all squared dx. And our right hand side, that is the equation 1 numbered here. And our equation 2, we had -pi over 2 alpha squared. What we want to do, we are equating both the 1 and 2. We want to do it in a way that we will get what was in the question at the latter part. So what we want to do is that if you notice very carefully, we are getting close to what we have in the question at the latter end. So what we would have to do is that we would have to divide both sides by -2. If you divide both sides by -2, your left hand side will become the x over alpha squared plus x squared all squared. That is what we have in the question at the left hand side. And your right hand side, when divided by -2, the negative will cancel the negative at the top. So you'll be left with pi over 2 alpha squared times 1 over 2 alpha, which will give you pi over 4 alpha cube. So what we're given, we've been able to show it in the other form, therefore it is true. So our question said if that, show that, this is it. So we use what we were given to show what they are asking us to do, and we realize that it is true. Therefore, the proof is correct. We've proven it. Please, are we okay?
Yes, please. But why is it that we didn't integrate with respect to the other term, which is
This one you
the
don't need to integrate, because if you look at the question you are giving, they didn't integrate it. They ended at, they still want the limit. You just have to do it in a way that they want it in what they gave you. We shouldn't proceed. If we proceed, we will not get what they asked us to find. We are not finding the final answer. We are just showing a proof. But we want to use the Leibniz rule. So for this particular question, all that we did was we just found for the partial derivatives. That's all. We didn't go ahead to integrate and then put in the limits. Please, are we okay?
yes, please.
All right. There's another question here. If I of alpha is equal to integral from 0 to infinity, the x alpha squared plus x squared plus alpha is equal to pi over 2 roots alpha, where alpha should be greater than 0. We are saying that use the Leibniz rule to show that integral of 0 to infinity of the x over x squared plus alpha all squared is equal to pi all over 4 alpha 3 over 2. I would want you to try it and let's see whether we are going to get the same thing. Please, have you noted the question? The question is beneath. Please, have we done writing the question? I want you to solve it and let me know what we are getting. Let's try our hands on it and let's see what we are getting. So all that we are doing is we are finding the partial derivative with respect to alpha for both sides. So the right hand side, it is a function of just one variable. So you find the total derivative with respect to alpha. So when you find the partial derivative with respect to 1 over alpha x squared plus alpha, what are you going to get? What are you going to get? And then you work it out in a way that you should get the latter side of the proof. Please, if someone is done, the person can stop or speak while listening. Please, I hello. Can you hear me?
Yes.
Hello. Hello. Please, can anyone hear me?
Yeah, we can hear you.
Okay. Please, I'm sorry, my network is messing up. So please, are you able to solve? What did you get? Please. Hello. 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 Hello.
Hi, madam.
Please, I'm asking what did we get as the answer? Hello.
Okay, madam, I got the integral of the x over x squared plus a all squared is equal to pi over 4 times a.
So is the what you did, is it the same as what they're asking us to prove?
Yeah. But I
So
think with the slide, there is some difference in it. So I don't know how it came up.
which difference, which part? Which part of it?
I think the equals the pi over.
They just changed it into a different form. They didn't use the roots. So we know that square root is the same as 1 over 2 power 1 over 2. So they just rewrote it in another form. What is it? Okay. This is what we are doing. So you had the integral of 0 to infinity dx over x squared plus alpha all squared equal to pi over 4 pi 3 over 2. Did you hear that?
With the other side, the right hand side, I got pi over 4 alpha 1 over 2 instead of the 3 over 2. I don't know.
How did you differentiate it? If you differentiate root alpha, what do you get? If you differentiate root alpha, what do you get? Because this one we have pi over 2 root alpha, and then the focus, we are doing the differentiation with respect to alpha. You have to bring the alpha to the top, and we know that pi over 2 root alpha, we can write it as pi over 2 alpha to the power 1 over 2. So when you move alpha to the power 1 over 2 to the top, you have pi over 2 times alpha to the power negative 1 over 2, and you apply a differentiation. The power, you would reduce it by 1. When you reduce it by 1, it will become negative 3 over 2. Are you getting what I'm saying?
Oh, yeah. With the negative, it seems, yeah. I didn't bring the negative.
So are we okay with the Lebanese rule for the examples that we've done? So the example, they'll give you something to show that the other thing is true. So you use what you've given initially, work it out to get it like what you have in the latter. And when you do that, you've proven it. Please, are we okay? So there's another example here. There's another example here. We have integral of 0 to infinity e to the power negative t minus e to the power negative bt all over t dt is equal to ln b, where b should be greater than 0. So for this, you go through the process, the Leibniz rule, the process. We are going to find the derivative. So first of all, we are going to find the partial derivative. Find the partial derivative of the function with respect to b. You are going to get e to the power minus bt dt. Then you integrate what you have with respect to t. You are going to get e to the power minus bt over minus b, and the limit is 0 to infinity. So wherever you find the limit is for the t, so wherever you find t, you put the 0 and infinity there, you are going to have 1 over b, and they are asking us to show that it is equal to ln b. So now you are now going to find the inverse of the derivative. So when you do that, you are now going to, more like you are going to integrate again. When you integrate again, you are going to have ln b plus c, and it implies that what we have is the same as ln b. Please, are we okay? Hello? Hello?
Are you there?
Hello?
Hi.
Hi, madam.
Yes, please, did you get the explanation for the next example?
Please,
We are
So
following, madam.
share it again. Like, it seems.
it is like what we've been doing already about the Lebanese. So you are going to find the derivative of I of b, and first of all, you find partial derivative with respect to b of the function. And I know that now you can find the derivative. So when you do it, you are supposed to get e to the power negative, sorry, you are supposed to get e to the power negative bt, negative bt. And now when you are done, you have to find you have to integrate what you have. When you do your over you are supposed to get e to get you integrate you test for the zero equation. B is Hello. 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 Hello.
Hello.
Please, I'm sorry, my network is unstable. Um, so we want to proceed with the application of differentiation. So we are saying that stationary point on a curve is where the gradient of the curve is zero. Thus, a stationary point or critical point of differentiable function of one variable is a point on the graph of the function when the function's derivative is zero. So we are saying that for applications of differentiation, we'll be looking at stationary points, which is the same as the critical point. It is the point on the graph where the gradient is zero. So an example, we have find the stationary point on the curve y is equal to 3x squared minus 18x minus 17. So what you will do is that you find the first derivative. When you find the first derivative of the function, it is going to be 6x minus 18, and then you equate it to 0. And then you find the x value, that is the value, stationary value. So the x value will be 3. When you are done getting the x value, you put it into the main equation in the question to get your y value, and that will be your stationary points. The x and the y coming together will form your stationary points. Is it clear? Hello.
Yeah.
My network is not good, so please be responding so that I know that I'm still on. Okay. So the next example is we have y is equal to 1 over 3x cubed plus 2x squared minus 12x plus 5. So for this one too, we have to find the first derivative. So when we find the first derivative, we are going to get x squared plus 4x minus 12. So you equate your first derivative to 0 so that you will be able to get your x values. So for this particular one, you are going to have two x values, and they are going to be negative 6 and 2. So you would put each value in the main equation you were given in the question so that you find your y values. So when x is equal to -6, our y value becomes 77. And when our x is equal to 2, our y value is going to be -25 on 3. Please, are we okay? So for stationary points, you find the first derivative, you equate your first derivative to 0, you find your x value or values. Then when you are done finding your x value or values, you put the values into the main question to find your y value or values. And that will be your stationary point. Please, is it clear?
Yes.
So we want to know check the types of stationary points that we have. We want to find the stationary points, types of stationary points that we have. So to find the type of stationary points, we determine the second derivative. So when you are done finding your first derivative, if you want to know the type of stationary point, whether it is going to be a minimum stationary point, a maximum stationary point, what you do is that you find the second derivative. When you find the second derivative and what you have, the value is greater than 0, it implies that it is a minimum stationary point. If you find the second derivative of the function and then it is giving you a value less than 0, then it is a maximum stationary point. If you find your second derivative and it is equal to 0, then what you want to do is that you find the third derivative. And when you find the third derivative and you realize that it is not equal to 0, then that particular it becomes the point of inflection. It's also a type of station. So it's either it is a minimum, a maximum, or it is at the point of inflection. So when you have a question and they ask you which type of stationary point is it, when you find your first derivative, the first derivative will give you your stationary point. The second derivative will tell you whether it is going to be a maximum or a minimum point. When you get your second derivative to be equal to 0, proceed to get your third derivative. And when you get the third derivative not equal to 0, then it implies that it is the point of inflection. Please, is it clear? Is it clear?
Yes, please.
Yeah, it's clear. It's clear. It's clear. It's clear.
So we have an example. This time we are being asked to find the stationary point and then determine the type of stationary point it's going to be. So the question is y is equal to x squared minus 4x plus 2. So our first derivative would be 2x minus 4. Then you equate 2x minus 4 to 0. Realize that our x value is 2. Then we now put the 2 into the main question, and then we realize our y value becomes -2. So our stationary point occurs at 2, -2. Now let's find the second derivative of 2x minus 4. What are we going to get?
2.
2. So 2 is 2. Since 2 is greater than 0, it implies that we have which type of stationary point?
Minimum.
Minimum. So that is all about
Minimum.
station. Okay, that is very true. So that is it. We have another example here. So we are being
This part is good.
come again.
I'm saying this part is good.
Okay. So this question, so we are being asked to find the stationary point and the type. So we have x cubed minus 3x squared plus 4. What will be the first derivative? What will be the first derivative? What will be the first derivative?
3x
3x squared.
3x squared
Mm-hmm.
minus 6x.
Okay, so what will be the x values when you equate it to 0?
Mm,
It's going to be 0 and 2, right?
Sure.
So when x is 0, you put it in the main equation, you realize that your y will be 4. When x is 2, you put it in the main equation, you realize that your y will be 0. So you would have two stationary points. So we would have 0 and 4 and 2 and 0. Now I want to determine the type. So let's find the second derivative. What do we get? What will be the second derivative? What will be the second derivative?
6x minus 6.
6x minus.
6.
So in this particular one, you realize that they didn't give you an absolute value or a particular value. So what you do is that you have your x values to be 0 and 2. So when x is equal to 0, what will be your d squared y dx squared? It will be equal to what? After finding your second derivative, we had 6x minus 6. Now I want to know to 0, what do we get? So this is what we had for our second
S.
derivative. And we solve for our stationary values to be x to be equal to 0 and x to be equal to 2. So I'm saying that when x is what will be your it's going to be -6 or hello. Please, are we there?
Yes.
Yes, we are there. We are
It's
there.
going to be -6. And -6 is less than 0, and this implies it is going to be maximum. That particular point will be a maximum, will have a maximum turning point. When x is equal to 2, we are going to have 6 to the bracket 2 minus 6, which is equal to 12 minus 6, which is equal to +6. And +6 is greater than 0. So for that particular point, we are going to have a minimum turning point. So when we have the stationary point 0 and 4, it will have a maximum point. And when we have the stationary point 2 and 0, we would have a minimum turning point. Please, are we clear?
Yes, please.
So the next thing we want to look at is the curve sketching. So under it, we want to look at asymptote. Asymptote. And we are saying that an asymptote to a curve is a straight line to which the curve
It's not that. Don't put it where you bath.
hello, approaches as the distance from the origin increases. Thus, as a straight line that continually approaches a given curve but does not meet it at any definite distance, can also be considered as a tangent to the curve at infinity. So under asymptotes, we are saying we have three types of asymptotes. We have the vertical asymptote, we have the horizontal asymptote, and we have the diagonal or oblique asymptote. So first of all, we want to look at what vertical asymptotes are. we say that the line x is equal to a, where a is a constant, is a vertical asymptote if the function f of x does not exist at x is equal to a. So for vertical asymptote, we are looking at the point on the graph for which the function does not exist. Yes. So all the x values, the x values that does not make the function define or exist. That is for vertical asymptote. So we are going to work on some examples to see what we are saying. So first example says that calculate the vertical asymptote of the following functions. F of x is equal to 1 over x squared minus 0. This is a rational function, q p over q, and we always know that q should not be equal to 0. So if you want to find the vertical asymptote for this particular function, you equate the denominator to 0 so that you will be able to find the point on the x-axis which makes the function undefined. So x squared minus x is equal to 0. When you factorize x out, you have x in brackets x minus 1 is equal to 0. So it's either x is equal to 0 or x is equal to 1. So it implies that our vertical asymptotes are x is equal to 0 and x is equal to 1. And it means that at this point on the graph, the function is what? Undefined. So if you look close on your right hand side, there is a sketch over there. It shows you a graphical view of the function that we have. So the blue dotted lines or short dashes show or tell us that they are the point at which the function is not defined. So wherever when you put 0 in this function, you realize that you're going to get 1 over 0, and 1 over 0 is undefined. And when you put 1 there, you're also going to get 1 over 0, which is going to make the function undefined. So that is for vertical asymptotes. Please, are we okay?
Yes.
Okay. So we have an example here. It says calculate the vertical asymptote of the function f of x is equal to x all over x plus 4. So the same thing, we have a rational function here. We are saying that the which is p over q should not be equal to 0. So our q in this case is x plus 4. When we equate x plus 4 to 0, we realize that x is equal to negative 4. And so our vertical asymptote is x is equal to negative 4. At that point, the function is undefined. Because if you put negative 4 in the original function, you realize that you're going to get x over 0. And if x over 0 is undefined. Another example, find all the vertical asymptotes of the function x squared plus 3x minus 10 all over x squared minus 4. So for this particular one, what they did first was you first of all factorized. When you do your factorization, you realize that some terms will cancel out. So you'll be left with f of x to be equal to x plus 5 over x plus 2. And our vertical asymptote will become x is equal to negative 2. If you don't do the factorization and you straight away start with the vertical asymptote, you are going to get x is equal to 2 and x is equal to negative 2, which is wrong. So because the numerator, when you do your factorization, you realize that certain terms will cancel. So the vertical asymptote is just 1. So it's not 2. So your vertical asymptote becomes x is equal to negative 2 after you are done with your factorization and then the cancellation. So that is it for this particular example. The next example says, find the vertical asymptote of f of x is equal to 4 over x squared plus 1. So as usual, this is a rational function. Our q, that is the denominator, should not be equal to 0. So if we equate it to 0, we want to determine our vertical asymptote, the point where the function is undefined. So when you do that, you realize that you are going to, it is not going to be, it's supposed to be x is equal to plus or minus I. It's going to be a complex number. So it implies that for this particular function, it does not have a vertical asymptote. It does not have a vertical asymptote, meaning that it exists for all real numbers. Every real number that you put there, it will be defined. So that is it for this example. Please, any question before we move to horizontal asymptote?
Please go backward. Let me ask you next. So if suppose the x squared, the plus is minus, how is it
Yes.
going to be?
When it is minus, when you move it across the equal to, it will become x squared is equal to 1. So you are going to have x is equal to plus or minus root of 1, which is going to be x is equal to plus or minus 1, which is going to be your vertical asymptote. So it's either x is equal to 1 or x is equal to negative 1. At that point, the function is not going to be defined. This is it, okay?
Uh,
Okay. So for horizontal asymptotes, we are looking at values on the y-axis. See, vertical asymptotes will focus on values on the x-axis, which will make the function undefined. Horizontal asymptotes looks at the values on the y-axis, where you have to take the limits of the function as x approaches infinity. So when you solve and then you are getting, so that is it about horizontal asymptote. It is looking at the values on the y-axis, which will make the function undefined. So what we do is you take the limit of the function as x approaches infinity. And when you work it out, you are going to have 3 different scenarios, and I think you will get there. When we get there, you see. So there is an example here that we want to look at. So we have f of x is equal to 1 over x squared minus x. We are being asked to find the horizontal asymptote. So what you do is you take the limit of the function 1 over x squared minus x as x approaches plus or minus infinity. So when you do it, the highest degree power is 2. You divide each term by x squared. You realize that you're going to get limit as x approaches plus or minus infinity, 1 over x squared all over 1 minus 1 over x. Now it's supposed to be this, yes. So wherever you see x, you have to place infinity there. So we are going to have 1 over infinity squared all over 1 minus 1 over infinity. And we know that any value divided by infinity will give us what? 0. So you are going to have 0 over 1, which is equal to 0. So for the horizontal asymptote for this particular function, it is going to be 0. So therefore, y is equal to 0 is the horizontal asymptote. Horizontal asymptote. Horizontal asymptote. Are we clear? Hello? Hello?
Yes, we are,
Hello?
we are listening.
I'm to Ado.
So we want to note something under horizontal asymptote. We want to note 3 things. So if you have a function and the degree of the numerator is less than the degree of the denominator. Example, the degree of the numerator is 1 and the degree of the denominator is 2. When you find your horizontal asymptote, always it's going to be y function. As far as the degree of the numerator is less than the degree of the denominator, your horizontal asymptote will be y is equal to 0. The second scenario, if the degree of the numerator is equal to the here, the degree of the numerator is 2, the degree of the denominator is 2, then your y, which is your horizontal asymptote, becomes x squared over 3x squared. You focus on the ones with the same degrees, and when you cancel the degrees out, you're going to have 1 over 3. So for the second scenario, you would have a particular value or a constant, if I should say. And the third the one, it tells you realize that which is a type of the numerator and the
Madam, we can't hear you.
asymptote, and you realize long division of as 4.
Please, madam.
Please, your network is
Asymptote.
Madam, please, your network is breaking.
Solve a function and said you make diagonal as
Hello, madam. Hello. Hello. Hello, madam.
particular value.
Hello. Madam, please, so your screen is not showing, and the network too is breaking.
A slant as So when you use the TV over 2, which is your son.
Hello, madam. Hello. Hello.
Oh, today network, what is happening? What? Oh, oh, listen me peninsula labi. Penalty miss. Zero. Ma Bernabé me kabel arafum buna 1.6.
Hello. Hello, everyone. Hello.
Hello, madam. Madam.
Ma.
The network,
Hi,
the
madam.
network is not helping. So please, can we look for another day so that we meet and then finish with this topic? Because I think the network today network is not good at all. That there is something small for us to finish.
Madam, I think
Is it
that's a
possible?
great idea.
Okay. So please, course rep, if the course rep is here, please talk to your people and get us the time in the day that you be available and it will be convenient to you so that we meet and then we finish everything now. Okay, so because of the network, let's end today's.
Okay, madam, we'll do that. We'll do so.
Okay, so let's end and continue next time. Bye-bye.
Bye. Bye.